All right. Hello, everybody. Today I'm going to be starting my AP Physics C videos. Essentially, what we're going to be doing for these videos is we're going to be going through each different section or each different topic that the course and exam description has for AP Physics C. Now that they've actually released their updated one, at least for the next few years, effective during the 2024-2025 school year, and likely again for a few years after that at the very least, right? Essentially, they've redesigned this course a little bit. They've broken up the topics a little bit differently than how the course and exam description had it between 2019 and 2024. And in addition to that, there are some new topics here and there as well. Some topics that go a little bit farther in depth, a few topics that go less in depth than they did in the past as well too. But essentially, again, we're going to be kind of going right from the top here. My goal is to cover one topic per video. Some of them might be a little bit shorter, some of them might be a little bit longer. If it is a video or a topic that does take too much time for one video, then I will be splitting that up into two videos as well. Uh, that could consist of theory in one video and examples in another video. It could be a mix of the two in each of those videos. But we'll just kind of see how it goes. But there's never going to be more than one topic introduced per video. So all that being said, AP Physics C now has, I believe, 13 units. Mechanics and then electricity and magnetism are designed now to essentially be going from one to the other, even more so than they were in the past. So mechanics covers units 1 through 7, and then electricity and magnetism just picks up right after that. So the first unit in AP Physics C is still kinematics. However, the first topic now, and let's go ahead and change color there, make it a little bit easier for you guys to read. The first topic, which is topic 1.1, right, unit 1, topic number 1, is actually just on scalars and vectors. So those of you who have maybe finished calculus, you might not need as much from this video. We're essentially going to be taking a look at if you take scalars and if you take vectors, how are you going to be able to calculate their magnitude? How are you going to be able to calculate their direction? The thing I've noticed is that College Board is starting to move a little bit more towards the IJK notation, and we're going to talk about what that is. We'll talk about a few different notations that vectors can actually have, and we'll talk a little bit about why the IJK notation is one of the better versions out there as well. It's something that actually does make a lot of sense, and it's something that almost helps you a little bit in terms of calculating magnitude and direction. Although the actual visuals behind it, perhaps not as helpful as some of the other notations. So let's start off by talking about the difference between scalar and vector. Most of you probably already know what this is, especially because I'm sure a lot of you have taken AP Physics 1, right? So we'll just kind of talk about their differences, and then we're going to be definitely focusing a little bit more on the vector side of things as well. So scalars are essentially any sort of quantity that just has a magnitude, or any quantity that can be associated with just a number and a unit. It has no direction to it, right? So magnitude is essentially how big something is, and direction, of course, is where something is oriented, right? A vector, on the other hand, has both magnitude and direction, right? It has some sort of quantifier as to how big it is, and it can be represented by something pointing a certain way, essentially. We model these vectors as arrows, right? So one way that I like to kind of think about vectors versus scalars, and it works most of the time, and I think actually it works every single time for AP Physics C. It's once you get into the higher level physics where it might not work quite so well, is if you can assign a cardinal direction to something and it makes sense, then you're dealing with a vector quantity. So for example, I could say that I walked 3 meters east, right? So if I walk 3 meters east, east is that cardinal direction. that is a displacement, right? That's something that has direction, it has magnitude. That is a vector quantity. We know that displacement is a vector quantity. However, if I just say that I walk 3 meters, well, where did I walk 3 meters, right? I could extend that and turn it into a displacement, but 3 meters on its own, that is just a distance travel. That is a scalar quantity with no direction. Likewise, if I wanted to say that something has, we know that units of energy are joules from physics one. If I wanted to say that something had 10 joules north of energy, well, yeah, that makes no sense, right? So energy, for example, does not fit under that vector category. It is indeed a scalar, right? So scalars, from things that we have seen in physics one, right? Energy is one of them. Work, of course, is the change in energy, although work done can be negative because work is something that changes energy, right? You can lose energy, hence work can be negative. It can't be assigned a cardinal direction. Much like energy, I can't say that I lost 10 joules of energy east, right? What that makes absolutely no sense, right? Mass, time, temperature, right? All of those things. We don't deal with temperature in physics C, but charge, for example, electrical charge, those are all scalar quantities, right? Of course, distance and speed fall under that as well, whereas things like displacement, velocity, and acceleration, as well as momentum, and all of their angular or rotational equivalents, right? Those all fall under vector categories. There's also something called vector fields as well, right? Every vector field that we're going to be dealing with here, you're going to hear the words throughout this series: gravitational field, electric field, magnetic field, right? Those are all vector quantities as well. In fact, they are what we call vector fields, where you can just take a space, fill it with vectors, and create some sort of mathematical function that tells you how big all of those vectors are and what direction they're pointing. That's a vector field. And again, we'll talk a little bit more about that when we get to that point. It's something that's a little bit more physically abstract than things like forces, which are also vectors. I don't know how I missed that on there. Right, they're essentially they're very similar to forces. They act almost in the same way. They're just a different way of looking at forces, essentially. All right. So all that being said, let's talk a little bit then about the different notations that you can see for vectors. So there's a couple of different notations. I'm going to stick to talking about two-dimensional until we actually get to the notation that College Board uses. Right, but some of you guys in your math classes, you've seen vectors that maybe look something along the lines of this. Let's say 2, 3, right? And you have those angular brackets there. That what those angular brackets actually show, and I am going to take advantage of this square grid that I've put on here just to make it look a little bit nicer. Here would be the vector, whoops, sorry, I went a little bit too far. Here would be the vector 2, 3, though. You go 2 units to the right, 3 units up, right? You start at the origin, although the starting and ending point don't matter. What matters is how far to the right you go, how far up you go. If I change that to -2, 3, instead the vector goes right -2, aka it goes to the left 2 instead, and then it goes up 3. So our vector would actually look like that one going left and up then, right? That negative again would mean going to the left. So that is one notation that you typically see for vectors in your mathematics classes. However, that is not the only way that you can actually represent vectors. You could also represent vectors, and this is something that you're almost never going to see in any sort of introductory physics course, but something if you do pursue farther studies in physics especially, is you're going to actually see vectors typically represented by this column notation right here, where essentially the x component, or the first part of your vector, is the top part of that column that we see right here, right? You see how the twos kind of match up there, and then likewise with the 3. So you'd have, say, the x coordinate on the top, the y coordinate right below that, and then if you had z, z would be right below y. College Board uses neither of those. What they want is for us to use the IJK notation. So what that actually looks like, and I'm going to get rid of this negative for right now, what the IJK notation actually looks like, the thing that you want to feel comfortable with vector notation is the x component, what the part that tells you how far to the left or right you're going, is followed by an I with a hat on top of it. And we'll talk about what that hat means in a little bit, right? Right after we're done writing the rest of this vector in its notation, right? And I'm just going to go ahead and call all of these vectors v. They don't represent velocity right now. V just means vector. We haven't talked about velocity yet, aside from just classifying it as a vector quantity, right? But the rest of that vector, that 3 then, the y component, is actually added to the 2 multiplied by this I with a little funky hat on top. And then you add 3 times j with a little funky hat on it. If you wanted to extend this to 3 dimensions, as might happen, and especially will when we get to E and M, you would actually have, in this case, it would be 0. That's not an O, that's a 0, and then multiply that by a k with a hat as well. What those 3 letters, that I, that j, and that k with the hat actually represent is they represent what we call unit vectors, vectors that have a magnitude of 1, and therefore the only purpose of that I, j, and k is to tell you the direction of the vector. How far are you going? Where's that 2 pointed? Where's that 3 going to be? Where's that 0 going to be? Right, and if you have a negative, right, just change that addition to a subtraction then, right? But if I have, for example, if I have a 2-dimensional space, again, we're not going to worry too much about 3-dimensional right now, and also I suck at drawing 3-dimensional. But you would have your x-axis, your y-axis, right? So what I hat looks like, I hat is again a unit vector. So it's a grid space of 1. It has a magnitude of 1. Therefore, it contributes nothing to actually telling you how big the vector is. Its only purpose is to help you with direction. Similarly, j hat, right, is pointed up along the positive y-axis. So I goes with x, j goes with y, and then, of course, k goes with z, which would be out of your screen right now if I were to try to draw that. But those just, again, tell you what direction your vector is actually pointing. So the way to read this is I go 2 units to the right, right? So the I hat tells you to the right, and then I say I go 2 units to the right because that's what it's multiplied by, and then 3 units up along the y-axis because that's what j hat represents. If I had -2 comma 3 for my vector, I instead would go -2 to the right, and then up 3, and you can see that that's actually equivalent to what we had with our previous angular bracket notation then as well. So it's a little bit kind of weird. You may or may not have seen IJK notation, as I like to call it, because there's an IJ and a K. But you may or may not have seen this in your math classes before, or in your physics classes before. It's not really something that I saw until I got to multivariable calculus when I was in high school. But it is actually kind of a nice sort of notation because that I hat, that j hat, and that k hat are all just constants then. So let's see how this actually works with vector addition then. I'm going to go ahead and add a new page, and let's go ahead and take a look at an example. Right, so I have 2 vectors, and because I cannot type like equations in this program that I'm using, and I don't want to like spend time writing out these problems, just know that if you see like I have a vector and I put an I, a j, and a k without the hat, those do represent the hat vectors. So if I say, for example, 2i, that's not 2 plus the imaginary number. What I really mean to say here is 2 times I hat. Hopefully that doesn't get confusing. I just want to try to make it a little bit neater, right, and not take up too much of your time with actually writing out these examples. So let's say that I have 2I hats plus 5j hats, and my second vector, let's say, is -7I hats, and let's put 7j hat there too. What I want to do is I want to find the uh, magnitude and direction of the resultant. And remember that resultant is just a fancy name for sum, right? It represents what happens when you add those two vectors together. The nice thing about this IJK notation is you can do subtraction in essentially an identical way to what I'm about to show you with addition, where you just take the components, the x components in Atom, take the y components in Atom, just like you did back in AP Physics 1 with your vectors. So what the resultant, I'll call that R, what that's going to look like is I have 2I hat, and I'm just going to write all of these steps out just so you can see it, right? 2I hat plus 5j hat, all added with -7I hat plus 7j hat, right? And so what happens now is, again, these are all just numbers. I and j hats are some constants that, again, only refer to direction. So you can actually rearrange this addition however you like. And so what I do is I group things with the I hats, so I can take that out, and then likewise with the j hats as well. So I would have 2 plus a -7 I hat, because both of those terms, the 2 and the -7 from both vectors, were multiplied by I hat, plus 5 plus 7 j hat. So it works exactly like the mathematical addition of vectors that we saw in Physics 1. Even if you didn't use the I and the j notation, if you're adding two vectors with the IJK notation, you still add their x components separately from their y components. The x, y, and z components are still all independent of each other. So therefore, my resultant is going to be -5I hat plus 12j hat. And I swear I did not plan this, but that actually is an easy Pythagorean theorem to do. So if I wanted to calculate the magnitude of R, that's just going to be -5 squared plus 12 squared, take the square root of all of that, because Pythagorean theorem. And that actually just gives you 13 units, whatever units that may be, right? That could be meters if it's displacement, meters per second if it's velocity, etc. Yeah, and then if you want to actually calculate the direction of it, well, let me go ahead and draw a little quick diagram here, right? So here's our origin, right, where the two axes intersect. I went 5 units to the right and then 12 units up. 4, 5, 6, 7, 8, 9, 10, 11, 12. So the resultant vector is going to look something along the lines of that right there. And essentially what I want to do is I want to find how far above the horizontal axis it's actually going to be. Well, in that case, I know the opposite of that angle, and I know the adjacent, right? The x and the y components are perpendicular to each other. So I can say that this angle is going to be given by the arctangent. I do prefer that over inverse tangent, just because inverse can sometimes be confused with the power of -1. Right, so this is going to be arctangent of 12 over 5. And essentially what that'll give me now is that'll give me some angle between 0 and 90. One thing to notice, I did not put the negative with the 5 in the arctangent. And the reason why is because, again, when I'm specifying my angle, I've drawn this picture now so you can actually see that if I get whatever angle that comes out to be, right, I'm going to go ahead and I'm going to be able to say that it's that many degrees above the negative x-axis. So let's actually go ahead and work that out. Let me go ahead and do that real quick just so you can see exactly what that looks like. So if I do arctangent of 12 over 5, that gives me 1.1 radians. So if sorry, let me go ahead and turn that into degrees for you, because degrees are the thing that we typically use. So that is going to give me a value of 67. That is not correct, is it? Yeah, it is. Yeah, that makes sense actually. It is about 67 degrees. We'll say 67.4 degrees above the positive x-axis. Sorry, above the negative x-axis. Um, and again, you'll notice that in the arctangent, there's no negative signs in there. And that's because with my picture, I don't need them. As long as I specify what that 67.4 degrees is relative to, it does not matter. It does not matter that that there's no negative signs in there, right? I just have to specify where that angle is, and I have done so in my answer here. All right, so that's it for topic 1.1. I know that that was kind of a little bit longer of a video. We kind of talked a little bit about what the structure of this series is going to look like, did a little bit of review, and then I spent a little bit more time on vector notation than I expected to. But I do think it is kind of just neat to see how all of those different forms appear, right? What they look like, just so you're prepared to see any of those vector notations when they do arise in your future. And then, of course, we took a look at a nice little example there too. But what you'll see, all in all, right, is that vector addition, vector subtraction, magnitudes, directions, they're not any different using IJK than they were with just considering X components or just considering Y components, right? The IJK notation is mainly, it has two benefits. One of the benefits is that you get to write the entire vector in this compact one expression, essentially. The second benefit is something that you're not really going to be really caring about, probably, but it has to do with what I mentioned, that the I, the J, and the K hats, those are all constants. So if I wanted to take a derivative, which is a calculus version of essentially like a slope, right? But if I wanted to take a derivative of a vector quantity, then that I hat, that J hat, and that K hat, those are all just going to remain constant. I'm not going to have to worry about how they affect a derivative or an integral. And so again, you're not really going to have to care about that too much. It does kind of help a little bit when we get to electricity and magnetism, and we revisit these hats in a couple of monstrous equations. But all in all, it's essentially just the notation that we have to know for this, and so hopefully it makes sense. But yeah, thank you for watching. The next topic that we actually have is displacement, velocity, and acceleration. And so essentially what we're going to be doing is introducing a little bit of calculus, right? We'll review the definitions of average versus instantaneous, talk a little bit about how position, velocity, and acceleration are related in terms of some calculus definitions then as well too. And then after that, we can move to the kinematics equations and essentially just talk about applications with those as well too. So thank you for watching, and I'll see you guys in the next video.